In this section, we're going to discuss rate laws. Reaction rate may depend on the concentration or concentrations of the reactants. The formula that describes how the reaction rate changes based on the concentration of the reactants is its rate law. We will first study the order of reaction for a single reactant, for which the order of reaction can be zero order, first order, or second order. One of the most important things we have to keep in mind is that rate laws can only be determined experimentally. They are not related to the coefficients in the balanced equation for the reaction. Rate laws are determined for a reactant by measuring how the reaction rate changes as its concentration changes. Initial rates are used because the initial concentration is known. One method of determining the order of a reaction is by graphing initial rate data versus concentration. The shape of the graphs made by plotting initial rate versus concentration indicates the order as described in the following slides. If the initial rate for a reaction stays the same when the concentration is increased, then the reaction is zero order. So if we increase the concentration of a reactant and there's no change in the rate, we would call that reaction zero order. If we double the concentration and then the rate also doubles, we would call that first order. If we double the concentration and the rate quadruples, we would call that second order. Remember, stoichiometry plays no role in determining the rate law for a reaction. These things are all done experimentally. Zero order reactions. If a reaction is zero order, that means it has the same rate at all concentrations of a given reactant. The rates of zero order reactions do not change as the concentration of the reactant is increased, since the concentration of the reaction is raised to the zero power. This means for a reaction with only one reactant, M equals 0. The rate law then would just be rate is equal to K, because again, just mathematically here, if I had this reactant A raised to the zero power, because it's a zero order reaction, anything raised to a zero power just simply reduces to 1. So it isn't included in the rate law expression. So we just get rate, where rate is the reaction rate and K is equal to the rate constant. There are no variables in this law. The rate is just the constant K. The graph here is just a line, horizontal line, with a y-intercept of the initial rate and a slope of 0. So as the concentration increases, as we go to the rate, concentration increases, the rate does not change. The rate remains constant. First order reaction rates are proportional to their concentration. As a result, reaction rate increases as concentration increases. The concentration of the reactant is raised to the first power, or in this case, that superscript, that M value is equal to 1. The first order rate law then is rate is equal to K times the concentration of our reactant A. Remember, we're raising this to the power of 1. This is a linear equation with the rate increasing linearly as the concentration of the reactant increases. So as concentration increases, so does the rate. And the y-intercept is the initial rate, and the slope of this line is K. So you can see right here, this is our slope, K. Second order reaction rates are proportional to the square of the concentration of the reactant. As a result, the rate increases dramatically as the initial concentration is increased, which you can see from the graph. In second order reactions, the concentration of the reactants is raised to the second power, or M equals 2. And the second order rate law would be rate equals K times the concentration of A, reactant A, squared. In summary, a graph of rate versus concentration can be used to determine the order of the reaction. If the graph is a horizontal line, then the reaction is zero order, and we know that the rate is equal to K, the rate constant. If the graph is a straight line with a positive slope, then the reaction is first order, and the rate is equal to K times the concentration of that reactant, which you can see that line here. If the graph has a quadratic curve, the reaction is second order, and the rate is equal to K times the concentration of that reactant squared. And you get this orange-looking curve upward here. Let's look at an example for a first-order reaction. We have this reaction 2N2O5, which decomposes to 4NO2 plus O2. We've seen this reaction previously in this unit. Concentration and initial rate data for this reaction is shown in the table. So we run 3 experiments. We have concentration of N2O5 and initial rate in molarity per second, all at the same temperature, 45 degrees Celsius. Okay. And you can see from the first 2 experiments, the concentration of experiment 1 is double that of experiment 2, is double that of the third, right? So we're just, from experiment 1 to 2 to 3, we're just halving the concentration of the reactant N2O5, okay? What happens to the rate, right? What happens to the rate in that case? Well, the rate goes from, we have times 10 to the minus 4 in every case here, so we can just look at this number here to see what's going on. We're going from 6 to 3 to 1.5. It's getting cut in half, right? It's getting cut in half. So every time we decrease the concentration by half, the reaction decreases by half as well. Decrease the concentration by half again, the rate is cut in half again. This indicates that this is a first order reaction. And so the rate law is equal to K times the concentration of N2O5. Example 1, understanding rate laws. Write the rate law using the experimental data shown for the decomposition of ammonia to nitrogen and hydrogen gas. So we see this reaction, 2NH3 produces N2 and 3H2. And then we have 3 experiments where we have 3 different initial NH3 concentrations and 3 different initial rates. So in the slides ahead, there's a lot of qualitative description of showing the concentration doubles here, what happens to the rate here. Before we look at that qualitative discussion, I also want to show you how to quantitatively set up a proportion to find this in case you ever can't quite see the relationship, or you want to just pick out a couple of experiments and find the relationship. So what we could say is the rate, the easiest one I think to see here is this one, because we can easily see that's double. So we could say is that the rate in experiment 2 is equal to K times the concentration of, I guess I know what it is, it's not A anymore. The concentration of NH3 to some power M that we don't know, right? Now we can set this up as a proportion where we can say the rate in experiment 1 is also equal to K times the concentration of NH3 M. And then more specifically, this is the concentration of NH3 in experiment 2. And this is the concentration of NH3 in experiment 1. Okay? And then we can substitute some values in. So the rate in reaction 2 is 3.2 times 10 to the minus 4, just reading that from the data table. Reaction 1 is 8.0 times 10 to the minus 5 is equal to K times the concentration of NH3 0.0088 to some M power. and then K times 0.0044. Okay, now this simplifies. We can do some simplification here. 3.2 times 10 to the minus 4 over 8.0 times 10 to the minus 5 is equal to 4. And then these k's cancel, and this simplifies to 0.0088 divided by 0.0044, which is 2 to some power m. Okay? So 2 to what power is equal to 4? M here is equal to 2. Okay? So we now know that it is second order with respect to this reactant. So the rate law is rate is equal to K times the concentration of NH3 squared. Okay, so there's the rate law. Now the answer is on the next couple of slides, and I'll review it with you. But there's an overall look at how you can solve these things quantitatively with the data that's given. Okay, so on the previous slide, I showed you quantitatively how to calculate these relationships between concentration and initial rate. But we can just look at the data and see that as the concentration of NH3 is doubled from 0.0044 to 0.0088, the reaction rate quadruples from 8.0 times 10 to the minus 5. If we multiply that by 4, we get 3.2 times 10 to the minus 4, indicating that this reaction is second order, and therefore the rate law is that the rate is equal to the rate constant K times the concentration of NH3 squared. So let's take a look at the summary here of the order of a reaction for a single reactant, which we're calling A. If A changes in any way and the rate is unchanged, we would call that zero order with respect to A. If we double the concentration and the rate doubles, or triple the concentration and the rate triples, in other words, if it's a one-to-one relationship here, then we would call that first order with respect to A. If the concentration doubles and the rate quadruples, or the concentration triples and then the square of that, the rate increases by 9 times, we would call that second order with respect to reactant A. Order of reaction. If there are 2 or more reactants, the order of the reaction, or the overall order of the reaction, is the sum of the order of reaction of each reactant, which are independent from one another. So, for example, if we have reactant A with M being the order with respect to A, and reactant B with N being the order with respect to B, the overall order of the reaction is the sum M plus N. Example 2 in this section on understanding rate laws. Aqueous ammonium and nitrite react to form nitrogen gas and water as shown by the chemical reaction on your screen. This is a balanced chemical reaction as written. We also see some experimental data for 4 experiments with varying concentrations of ammonium and nitrite. There are 2 reactants here, okay? So we have data for initial concentrations for both reactants, and then we're also measuring experimentally the initial rate of the reaction. So examine the data and write the rate law for this reaction. Keep in mind that you need to examine data for each reactant independently because both reactants do not have to be the same order. So, similar to the last example, there are some qualitative looks at this data that determine the rate pretty quickly in the following slides, as you can see here. But I'm going to show you quantitatively how to determine this first. So we need to find the rate with respect to each reactant separately. So the first thing I'm going to do is look at the NH4 plus. So let's start with reactant 1 being NH4 plus. Okay? Now, we have to make sure if we're looking at NH4 plus that NO2 minus concentration needs to be constant. Okay? Needs to be constant. So I have two options here. I can look at experiments 1 and 2, or I can look at experiments 3 and 4, because in those cases, NH4 is changing, NO2 minus is staying the same. It doesn't matter which ones you choose. Just for ease, I'm going to pick experiments 1 and 2. Okay? So remember, we can say the rate of the second experiment over the rate of the first experiment equals K times the concentration of NH4 plus for the first experiment over K times the I have that backwards. Hold on. Anybody catch that mistake as I was writing? The second experiment over NH4 plus for the first experiment, okay? And the other thing I forgot was we have to figure out to what order this is, right? So that's what we don't know. Some order will give the letter N, right? So that's what we're solving for, finding the order of that reaction. Okay? So now we can substitute some values. So the rate for the second reaction is 5.4 times 10 to the minus 6 over 2.7 times 10 to the minus 6 equals K times 0.200 to the N power over K times 0.100 to the N power. And the simplification here is 5.4 divided by 2.7. This is 2 equals 0.200 over 0.100 is 2 to the N power. So in this case, N is equal to 1. Okay? In this case, N is equal to 1. So that's important. It is first order with respect to NH4. So what we could say is for the first reaction is that the rate is equal to K times the concentration of NH4 plus to the first power, right? Which of course we generally don't write our power if it's a 1, right? So this is how we would write the rate with respect to NH4. So I'm going to stop here, summarize this answer on the next slide before we move on to looking at the second reactant, NO2 minus. All right, so this slide just summarizes the quantitative work we did on the previous slide. We did compare experiment 1 and experiment 2 to show that when we double the ammonium concentration, the initial rate also doubles, which means that the reaction is first order with respect to NH4. All right, now let's figure out what order this reaction is with respect to the nitrite reactant, NO2 minus. So I've highlighted here experiment 1 and experiment 3 because the NH4 concentration is remaining constant. So we're only studying an effect or a change on one reactant at a time here. So for the NO2 minus, So I had written the equation on the previous slide for the rate. So if you want to go back and watch that, you can. I'm just going to use it here to set up the proportion and say the rate for experiment 3, 5.4 times 10 to the minus 6 over the rate for experiment 1, 2.7 times 10 to the minus 6 equals K times the concentration in experiment 3, which is 0.200, to some order, which we'll call M. And this is the first experiment. So we look here. This is 5.4 divided by 2.7 is 2. And then this substitutes down to 2 to the M power. And in this case, M is equal to 1. Okay. So when NO2 minus doubles, the initial rate doubles, which means that the reaction is first order with respect to NO2 minus. So bringing over the previous rate law, where we found that it was first order with respect to NH4 plus, I have a subscript of 1 here that I'm not writing. I can write the same thing for the concentration of NO2 minus. On the next slide, we're going to look at how we can use the experimental data to determine the overall rate of the reaction. All right, so let's compare now what happens when we double not just one reactant at a time, but both. So between experiments 1 and experiments 4, both the concentration of NH4 plus and the concentration of NO2 minus are doubled. And what happens to the rate here? 1.08 times 10 to the minus 5 divided by 2.7 times 10 to the minus 6 is 4. So the rate is quadrupled, which means that overall, if I'm doubling the concentration, but the rate is quadrupling, then the reaction overall is second order. Because the data show that the reaction is first order with respect to NH4 plus and first order with respect to NO2 minus, even though they are not written, the exponents on the reactant concentrations are 1 and 1. So I have a 1 here for first order and a 1 here for first order. Of course, you don't write those because any value raised to the first power is just that value, right? The overall reaction order then can be found by simply adding the exponents on the reactants in the rate law. So 1 plus 1 in this case is 2. So the reaction is second order overall. All right, here's example 3 for understanding rate laws. We have 2 NO gas plus 2 H2 produces N2 gas plus H2O gas. Experimental data has shown that the reaction above is second order with respect to NO and first order with respect to H2 based on the observations listed below. If the concentration of NO is doubled, the rate of the reaction will quadruple. So that means it's second order. If the concentration of H2 is doubled, the rate of the reaction will double. That means it's first order. If the concentration of both reactants is doubled, the rate will increase by 8 times. What is the overall rate of the reaction? And write the rate law for the reaction. So the overall rate of the reaction is just 3. 2 plus 1, which is 3. But we're going to use the rate law to demonstrate that. So the rate is K times the first reactant is NO, and we're told that if it's doubled, then the rate will quadruple. So that's second order. So we need a 2 here. And then if H2 is doubled, the rate will increase, will double. So that's first order. So we have a little 1 here that we don't write. So remember that the overall rate of the reaction is this 2 plus 1, which is third order overall. But I just want to show you why that's true. Because if we say the rate is equal to K times the concentration of NO. So it says in this last bullet point, if the concentrations of both reactants is doubled. So I have 2 times the concentration of NO. And then, of course, this whole thing is being squared. And then I have 2 times the concentration of H2. And, of course, this is just raised to the first power. What factor is the rate changing by here? So it's 2 squared, which is 4, and 2 to the first power, which is 2. So 4 times 2 is 8. So the rate should be 8 times the original, which is what we get here. So we have an overall third order reaction with this rate law. We'll review this on the next slide. So in answering the question, what is the overall order of the reaction? This is a third order reaction overall. The overall order of the reaction is just equal to the sum of the two exponents, m plus n. M is 2, as shown in the rate law here. N is 1, and so the overall order of the reaction is third order reaction. And then the other thing we were asked to do was write the rate law. I showed you that on the previous slide, but here it is typed out if you'd like to review it. All right, let's look at a summary of the order of a reaction for 2 reactants. So if we have the order of reaction A, if we keep that all zeros, and the order of the reaction with respect to B, just increasing 0, 1, 2, then the order of the overall reaction is just the sum. So in this case, we would get 0. In this case, we would get 1, and then 0 plus 2 is 2. If the order with respect to reactant A is 1 and B is 1, then the overall order is 2. If the order of the reaction with respect to A is 1 and B is 2, then the sum is 3. And if the order with respect to A is 2 and the order with respect to B is 2, then the overall order of the reaction is 4. This represents all the possibilities for 2 reactants, since which reactant is labeled A or B is arbitrary, so any 2 reactants. Fourth order is the highest order of reaction in this course.